Hello and welcome to Math 253. In this video we will be looking at checkpoint 5.47. It says using the substitutions x is equal to u and y is equal to the square root of u plus v, evaluate this double integral over r of y times sine y squared minus x dA, where r is the region bounded by the lines y is equal to root x is equal to 2, and y is equal to 0. So the first thing we probably want to do is we want to figure out what this region looks like. We have the sideways parabola, y is equal to x, or y is equal to the square root of x. We have the vertical line x is equal to 2, and the horizontal line here y is equal to 0. And so that's pretty clear what our region should be. Now what we want to do is we want to imagine what this region will look like on the xy, or I'm sorry, on the uv plane. And our transformation t takes our x values to u and our y values to the square root of u plus v. So ideally we would take points to points to see where they map up, and we probably would be interested in figuring out what the pullback is, or the t inverse function is, so that we can see how the mapping goes. But what we're going to do instead is we're going to take a look at line segments, this line segment, this line segment, this line segment, and see where that goes as we bring it over to uv. We're still going to need to know what the inverse transformation is. So the inverse transformation tells us we need to find u is equal to and v is equal to functions of x and y. Well, clearly x is equal to u, so u must equal to x, so that is one of them. And to figure out what y is equal to, or what v is equal to, we have an equation here that has a v, so let's take that equation and let's figure out what y is equal to. Now u is equal to x, so y is actually equal to the square root of x plus v. And we are solving for v, so let's square both sides. So we get y squared is equal to x plus v, and then when we solve for v, it's just bringing the x over to the other side. So that's y squared minus x. And I'm kind of looking ahead a little bit, and I just noticed that there's a y squared minus x in there, so that whole expression in the sine function will just be v. All right, so now that we have that, let's figure out where this transformation takes each of those line pieces there. So let's start with, since x is equal to u, let's take this x is equal to 2 line and transform that to y is equal to 2. So x is equal to 2, let's write it down here. X is equal to 2 means that u is equal to 2, and that line u is equal to 2 is just a straight line, vertical line that passes through this u is equal to 2. Okay. The other one that I think might be easy, I don't know, but we have y is equal to 0. So let's take the y is equal to 0 line. When y is equal to 0, we have, let's see, what's the equation with the y? Here's a 0. V is equal to 0 minus x, but x is equal to u, so v is equal to negative u. And that looks like it's just going to be a diagonal line. V is equal to negative u. All right. Now let's figure out what happens to this curve, and that is the curve y is equal to the square root of x. So when y is equal to the square root of x, this looks like it's the term with a y in it. So let's square both sides. this could be seen as y squared is equal to x. So we put that into y squared, so that's x, but then there's a minus x there. So I think I'm just going to get a v is equal to 0. What is v is equal to 0? V is equal to 0 is the horizontal line. And I think we have our region. So if this is the region R, this is our region S that we're going to integrate over with respect to u and v. And just to remind us about where things happened, we have the line x is equal to 2 that became u is equal to 2. We have this line y is equal to 0. Y is equal to 0 became v is equal to negative u. And then we have this curve, y is equal to square root of x, and that became v is equal to 0. And so those are the three boundaries that we had in x that we now have in y, and so we have this region. We can attack this region as a type 1 or type 2 region. I think doing this as a type 2 or type 1 region would be a little bit easier because you will have a 0 for one of those components. So if we do this as a type 1 region, we're going to integrate with respect to the horizontal axis or the vertical axis first, and we draw a line parallel to that axis. We're going to enter through v is equal to negative u, and we're going to exit through v is equal to 0, so that 0 is always nice. And then our u limits are going to be constants, and that just starts here at u is equal to 0, and I believe this is u is equal to 2, so 0 to 2. Okay. So we're almost ready to redo our integral, but before we do that, we're going to need the Jacobian. So let's find the Jacobian. Jacobian is going to be a set of partial derivatives and our functions x and y with respect to our function or variables u and v. So derivative of x with respect to u, derivative of x with respect to v, derivative of y with respect to u, derivative of y with respect to v. And if we take the derivative of u or x, sorry, we were looking at this set of equations, the derivative of x with respect to u is 1, the derivative of x with respect to u is 0. The derivative of y with respect to u, let's do that off to the side here a little bit. dy du, if we look at u plus v to the 1/2 power, is going to be 1/2 u plus v to the negative 1/2 power times 1. And that's going to be the same for both of them. So I think this is going to be 1 over 2 square root of x plus, or square root of u plus v. U plus v, and then 1 over 2 square root of u plus v. And to find the determinant, it's just going to be 1 times 1 over 2 square root of u plus v minus 0. So that's it. That's our Jacobian. Okay, let's get this function copied down here. And then now we're off to write this over S. Now we have a y. Ooh, what's y equal to? Y is equal to the square root of u plus v times sine, and this is what we noticed earlier. Y squared minus x is actually just equal to v, so we can do the straight substitution for y squared and x, but we have the whole y squared minus x already figured out there. And then we're going to integrate with respect to v first and then u. oops, let's not forget our Jacobian. Our Jacobian is going to be 1 over 2 square root of u plus v. And then now we integrate with respect to v first and then u. Okay. And as we do this, we could see that these things cancel, which is great news. And I just have a 1/2 and then my double integral of sine v. And the v limits has to be on the inside because the limits are not constant. That's negative u to 0. And then the du goes from 0 to 2. All right, we integrate sine with respect to v. The integral of sine is, I think it's negative cosine v, and we're going to put negative u and 0 in. 0 first, so that's negative cosine of 0 minus negative cosine of negative u. Quite a bit of negative signs here. Cosine is an even function, so the cosine of negative theta is equal to positive cosine of theta. So we can just knock this sign out, and these two will make it positive. And a cosine of 0 is 1. So I have a negative 1 plus cosine of positive u. All right, now let's drop the rest of the other stuff that we have. That's a 1/2 integral from 0 to 2 du. And so this will be a 1/2, and I have a minus u plus u squared. Oh, the antiderivative of cosine is positive sine u. We're going to evaluate this from 0 to 2. We're going to get a 1/2, and then we're going to get a negative 2 minus sine 2, and then 0, 0, so that's zeros all around. All right. Oh, this is a positive, and so we can just switch the order. This is going to be 1/2, and then a sine 2, and then plus 2. Oops, maybe we'll put a parentheses around the sine 2 there, and then that's it. All right, I hope that helps. Good luck.